Hello, it's James from XRobots.co.uk. This is part 2 of my Star Wars Power Droid project. Yes, we're going to make a real biped walking android, and I've built a few before, which I discussed in part 1, so check out that part for a full explanation of the whole project and a recap on some of my older walking projects. Now I'm going to take some of the inherent mechanical design that was in Android 11, which worked pretty well, and there's a recap of that in part 1, and you can also see some video of this being built and operating in my channel from quite some time ago. And we're going to make it the size of Android 12, which was quite a bit bigger. It's about 3 feet tall. It didn't work as well for reasons that I've detailed, but hopefully with the same mechanical design and a modern microcontroller like an Arduino and a modern inertial measurement unit to keep it stable, we should be able to do a pretty good job of it. So if you can imagine something about this tool with a box on top walking around, that's what it's going to be like, and it's going to look like a Star Wars power droid. Hopefully we can get some of that special conduit to go over its legs with any luck. The first mechanism I want to consider is the one that tips the ankles and the hips sideways, and in this android I use servos which are around the back here, and they just pull a rod up and down that tilts the bottom of the leg here against this pivot point, which is front and back. Those are pretty puny servos, and it works okay for something this size, but as I described last time, if we scale up twice the height, we're also scaling twice the width and twice the depth, so we actually end up with something 8 times bigger that needs 8 times as much torque. Hence we've got some fairly hefty motors, and we still need to put external gearing on those. So we need to make an equivalent mechanism to tilt this and see what we can get out of this in terms of force. And I'm going to test that by building it and grabbing hold of it to see if I think it's enough. So the plan is to put a small gear on the motor, which is the one on the left, and I've left space for a captive nut there so we can put a nut in a little screw thread to hold it on the flat of the motor. I've got these gears out of the gear library in Autodesk 123D. You do have to pay $10 a month to access it, but it's quite handy for doing quick gears. I've got the biggest and the smallest here. The biggest one is 24 teeth and the smallest is 8. I think it might not be big enough. In which case we'll have to do something else, but for a quick test it's okay. So the basic plan is to have the motor running round a bigger gear, and that will give us some further leverage. Now since we're actuating the ankle joint, in fact it doesn't need to spin round and round and round, it only needs to move a little way there so the android can lean left and right. So in fact we only need a portion of the big gear, and the aim would be to fix either the big gear or the motor with the little gear on and have the other one rotate around it to actuate that joint. I've just put together a plate here which is for the motor mount, and that's got the holes in the right place and one in the middle to let the motor shaft out. So now I've stretched out that mounting plate, so we've got a hole that allows the big, or the portion of the big gear, to turn in the same place, and obviously the little gear is attached to the motor that's mounted on those 4 holes. So the result obviously of the motor turning is that this section of the big gear will move. And I've got quite a bit of distance there, obviously it's 45 degrees there, so that's more than enough than I need the actual joint to move. Obviously it can't run right to the end, right to this edge, because the gear would fall off, so it's probably going to run to the last kind of dip in the gears there, so that we've still got lots to hold that in place with. And just to test torque, I've added this large piece on here, so either that would be the part that the front or back axis of the ankle is mounted on, or we turn the whole thing around and that will be mounted on the foot, and then the motor would rotate around and the blue part would have the front to back axis on. But let's put this together and hopefully I can offer this up to the robot and we can explain a bit more how it looks. I've printed those parts out. You may have seen I've printed some spare little gears, and I'm going to use those in another mechanism in a moment. But essentially what we've got is the motor attached with some countersunk screws. I've only put 2 in because I only had a limited amount of short enough screws. So the motor's fixed on the back there. We've got this pivot point, which is just a bit of studding with a nut on. Obviously in the real mechanism this would be much longer, and it would be double braced at both ends of the foot pivot piece. For now I've just stuck that there for testing how much force and how much torque we can get out of this. So the gear is attached there with a captive nut. We've got a bit of 4mm studding in there with a slot cut in the end so that it's screwed in against the nut in that hole, and that holds it on the flat of the shaft. So I should add that this isn't back drivable. These motors have got worm gears in, so I cannot push that backwards. And if I push this piece on, then of course I cannot drive that backwards either. There's a little bit of slack in the gears there, so we need to just adjust up the position of these two things by a small amount. Pretty much the same as when I did Ultron, we just need to fine tune it, but essentially this thing is locked solid, so when I position this in a specific position it will stay there with no power, which is really important. If we take a normal radio control servo, then of course these things are back drivable, and they've got their own internal PID controllers that try and make them move to the position you want. Then obviously if you put force on them, it will back drive the motor, and the servos sit there buzzing, applying more power, getting hot. And of course that won't happen with this, it will just go to that position, stop, then it's mechanically locked essentially. So I'm going to power this up and see how fast this moves, and whether I think there's enough force there. And of course I've got the option of putting in a bigger gear here and moving this whole thing out, and we can compare the size of that with the other Androids shortly. I've just wired this into an 11.1 volt LiPo like this one, and that's just out of shot here. We've got a couple of leads linked to the motor, and as expected it's got quite a lot of power to it. It's also pretty quick, so we can even gear down even further if we want, but if I just energise this, we can see it moves fairly satisfactory. And given that that's actually the Android leaning side to side, it's probably far too fast. Obviously it'll be speed controlled and PID controlled, but it does mean it's quite agile, so even if I move this distance out, we can still get enough speed probably. And there's definitely enough torque in here, so if I just take this to one end, and then let's just pop that back in there and hold on to this and try and stop it. I can't stop that with my hands if I grip it. It's still very tough indeed. So that's pretty good. We could use this at the hips as well, but let's see how big that is in relation to what we're trying to build. So if we compare that to the size of the existing Androids, obviously the pivot point is on the inside here, so we get that bigger distance on each side, and the servo pushes this rod which is made of a bolt. So if we compare that to what we've just built, that's actually about the same sort of distance, even though we're trying to build an Android twice as big. Whether its legs are twice as fat, I guess we can get away with that, so we can increase this leverage angle to double, which means we'll get half the speed and twice the torque still, which should be more than enough, and I think it will be fast enough. Obviously we need a different way of generating the gears, but that's not too much of a problem. So on this Android, of course, we don't have any side-to-side axis on the ankles, as I mentioned last time, which is one of the reasons it doesn't work. But if we can imagine those legs being about twice as wide, and that mechanism being twice as wide, that should work out. And the intention is, of course, that this is either stuck down, and this thing moving, leaning side to side, is this side-to-side pivot, or that thing is fixed down, and the motor rotates around it to give us the side-to-side pivot. Then, as I said, mounted on that, we get the front-to-back pivot, the other joints in this axis to give all of those leg movements. And of course we could use that same mechanism in the hips if we don't use something else to do the same thing here, where we've got this other servo, a pivot point here and that distance, so we could employ exactly the same mechanism. But let's have a look at something else now, which is going to be used in the side-to-side axis, and it could be used in the other joints as well, which would be more of a linear actuator. Here's a really simple linear actuator that I've just put together for testing. So obviously the gear is attached there to the motor with the 4 mounting holes in the same way, and as it turns the rack will slide up and down. It's pushed against the gear with these red rollers, which are going to be some bearings with a 6mm inner diameter. So let's get that printed and see how well it works. There's going to be some other practical issues, of course, like the rack falling out of the top. Here's my assembly. So again, I've got the motor attached there on the back, and we've got 2 bearings there and the gear that's attached to the motor, and I've got the rack here, so that pops in like that. And obviously as the gear turns, it goes backwards and forwards. And it's exactly the same gear pitch as the last thing I made, so it should give me pretty much the same amount of force, but obviously it's linear force instead of torque. So if we just connect up the battery again here, should see that slides up and down, and it's pretty tough. In fact, if I try and stop that with my hands, well, apart from the rack falling out, pretty much I almost can't stop that with my hands. So It's a pretty tough assembly, so that will be more than enough force to force that parallelogram assembly to shift. So let's just have a look again at what the principle will be of using this type of actuator. In the side profile, the legs are basically parallelograms with, it's essentially a double hinged knee with these two rods, and each one is a 4-bar link. So I've made this little 3D printed model. So of course they shift like this. So we could use a linear actuator to push across between the corners perhaps that get further apart and closer together. So obviously my actuator would need to go across this, so we'd have to mount it somewhere there and have a pivot point at one end and a pivot point at the other end of the rack so that this can rotate. So of course as this gets closer together and further apart, these points here would need to rotate on 2 more axes, and then that can push the assembly around. The problem that obviously you've seen here is that the rack pops out, so it's got rollers holding the bottom and this gear drives it up and down, and that holds this in the middle quite well. There's nothing to stop it popping out this way, and obviously this is just scraping along the plastic flat to flat at the moment, and we really need another pair of bearings at each end holding this in the middle to reduce friction and to make sure that that runs properly and doesn't come out. So we'd be looking at, what's that, so 2 bearings there, another 2 here and another 2 here, so that's like 6 bearings to hold the rack in place properly. And then obviously 2 more pivot points, so another pivot point here and one at the end of the rack. So that's getting quite complicated and it's going to end up quite bulky. So I decided to think again about whether actually this is really a good idea, and it was the way I did Android 11 with servos pushing across the parallelogram, but essentially each corner of this rotates. So why can't we use this much simpler assembly to do the same thing? So obviously of course it's much simpler with just one piece fixed down, a nice double braced hinge point, and we can space everything out with washers, and then the motor just runs around it. That's much simpler than all of those bearings and all of those hinge points. So perhaps we could put that on one corner here, and we could extend out obviously the radius of the big gear to give us the leverage that we want, to give us the right torque and speed. The only problem is of course with the legs having to be quite skinny, and this rotating in both directions, at some point the gear's going to stick over the edge. So we can end up with this unsightly thing sticking out. So then I started to think again about perhaps we could build this whole assembly further into this, because there is quite a distance between the front and back uprights of the leg. So perhaps the whole thing could fit somewhere in the middle. So taking the same parallelogram, if we just draw that out so I can draw all over it. So essentially we've got this thing with hinges in the corners. And as I mentioned, if we were to put this on one corner, we need to have effectively a radius from here. Looks a bit like that. And then a gear that sort of sits here on the motor that runs around it in either direction. So that means it can go backwards and forwards, but the gear needs to stick out. So what if we move that gear along? What if we put in another parallel link in the middle, and we put the motor on there, and then we put the gear kind of in the middle here? That would still follow the same line as this whole thing moves. So the motor would move across and it would follow the same arc. So that would be one way of doing it, but then we still need these 2 parallel links here. Just to get that motor close enough, because if the motor's right at the top, it doesn't reach, or at least the arc here would be too small to have any effect. But then I realised that was stupid, because obviously these sides are closer together than this is. So why not just put the motor here where this hole is, and put the gear on the other side, and see what happens there. So obviously that's pretty much ready made for us. So if we do this, and then we actually conveniently put a hole in here so I could plot the circle with the pen there, that gives us a nice arc, which you can see there the thing follows perfectly. So if we put the motor here and we had the larger gear attached to the other side, that would work pretty much just as well, although this arc's quite big, so I'm not sure what's going to happen in fact if I move the motor over. So if we had a lump sticking out of here with the motor on, would it still follow the same arc, or what would that radius be? So I made another one that's got a lump on with the hole in, so I can plot that. So let's see what that does, and see if we get the same linear shape, or what do we get. So there's roughly the shape there. It seems to be a curve and follow properly, but what's the radius now? And having experimented with this already, I can tell you that the radius is actually this. So if we get this square, we put a mark in there roughly where the middle is, one roughly opposite, and then we put this piece like so and hold the corner down, we'll see in fact that this screw perfectly follows the radius. And the middle of that is about there. So if we place that back on, which was about there, we can see in fact the radius is now offset, and it's only offset by this distance, curiously. So in fact all we've done is just shifted the radius over. So if I put the motor even further out, then it would be exactly the same radius, but the centre of the radius would be about there. And again, that would give us the same radius that follows on this length of the bar. So I thought while I was making scale models, I might as well make one the right size for the Android. So I've made this slightly taller one, and then we can offer that up to Android 12 here and see how that matches the size of the leg, and it should be about right. So that's roughly the right size for the top and bottom of the leg, obviously with the other spacing of the double hinge knee and the other axis at the top and the bottom. So let's do a plot of that and see what we get. So I've conveniently got the pen hole again, so I can just draw the arc there roughly. So we can see that now this is obviously much taller. The arc there fits very neatly inside here and would continue off to be this sort of shape. There we go. So obviously if you can imagine this being the top of the knee and it can bend this much, then this gives us quite a lot of knee bend there. So there's more than enough to pick its feet up. It probably doesn't even need to bend anywhere near that to walk, and then pushing the leg backwards would go that way. So that's more than enough of a mechanism, and obviously plotting this is the full distance it moves as well. So I'm going to make another one of these with an arc on one side and a representation of the motor on this side, and we can just check that that all follows correctly. I've printed this demo piece, so we've got the small gear on the motor is represented by this circle with its centre there, so slightly offset from the main upright here, and the big gear is of course this, and that will be the centre there, and this radius here is exactly the same as this radius, but obviously we don't need the rest of the big gear, so we can throw that away and we just keep the rest of the piece inside that we need. So if you can imagine that being the top or bottom of the leg, and as it bends to bend the knee or push the leg backwards, the small gear tracks the big gear perfectly. Obviously the joints in the real one won't be dodgy screws in the hole, they'll be nice and tight and on bearings or something similar, but we can see that tracks perfectly. So that seems like a really good solution, and of course we'll get total linear force or torque around the corners as this turns with this curved track, and of course the gears will be held together because this is all in one assembly. So that seems like a really good solution. So obviously I need to print a much bigger gear here than the biggest gear in the gear library in 123D, which is this one. If I just pop that off there, we can see that that's obviously far too small. So we could just scale up these gears, and we could scale up the little gears to maybe 2 or 3 times the size. But obviously that will just keep the same tooth ratio, so it won't actually help us very much. What we really need to do is have a gear with the pitch of these teeth and just have many more teeth, and keep this gear the same size on here, and then we'll get a much better ratio, and that will multiply the torque up. So we need to find another way to generate the gears. I found this website called geargenerator.com, and this will allow you to generate gears, and they're all animated nicely here, and then we can download an SVG which we can then import to make those into 3D objects. So there's various settings here. You can go and you know, up the number of teeth and things like that on whichever gear you want. We can select different ones and we can modify them. We can select the pressure angle of the gear, so we can make that a much sort of stiffer angle, if you like, to the gear, and we can do all of the settings, and we can add them and make a complete gear chain with sort of you know, a smaller gear in the middle and all sorts of things. But if I go and get rid of some of these, so let's there we go, we'll just leave ourselves with one there. Perhaps we'll have 30 degrees back on there, which was the same as the others I generated before. Maybe some more teeth, and we can download an SVG there, which it will just save. What I found though is that in fact they won't import directly into 123D Design. It says they're invalid, and that's because there's lots of other features we need to delete first. So I've got this program called Inkscape, which is in fact free, so it's quite a good image manipulation and drawing tool. So we can go and open up that SVG. Let's just go and get that. Oh, there it is. And then we can delete things. So we've got things like these extra kind of features, the text that we've got on here, we can delete that red dot. And And that should just leave us with the outline, and then if we go and export an SVG from there, we can import that into 123D design. So I've already imported it there, but if we go to the menu and do import SVG as a solid, we can select the modified SVG, and that'll automatically extrude it into an object for you. There's no center hole in it, but it's easy to find just by getting a cylinder and going and snapping that into the middle. So if I get the snap tool and place that there, it puts it perfectly in the middle for you, so then you can extrude that through and subtract it from the main gear, and that will give us the center point for the pivot. So that's a pretty good way to make gears of any size, of any number of teeth you want. You can make them absolutely gigantic if you want, so I should have no problem designing the gears and getting them into 123D design to design that mechanism. So I'm pretty glad I've worked my way through this bit of R&D and come up with this mechanism, and I'm surprised I'd never thought of it before. I've built quite a few androids that use this parallelogram leg design all the way back to Android 3, 4, 5, 6 and 7 I think, and 11 and 12. So surprising I never come up with that, but there we go. That's what you get for experimenting and working things out and trying actually building mechanisms to see what happens. That's the same reason I did lots of R&D at the start of Project Ultron, so don't forget to check that series out. The early episodes again are experimenting with mechanisms and sensors and so on. So it looks like I'm probably going to use this mechanism for the side-to-side tilt of the ankle and the hips, and obviously right up in the body we've got lots of space for this leverage angle and the big gear, and in the ankles we can put them on the side with that longer leverage angle, probably a gear twice as big as this, made with the gear generator. And then we can do the same thing with this in the side profile. So next time I'm actually going to get on and start designing the actual parts, and hopefully we can get an ankle or something like that made up. So don't forget to subscribe for more updates on this project and other projects, and also check out the social media links in the description to this video.